Okay, in the previous lecture, we have established that for a system of particles, we can work with angular momentum and the angular momentum satisfies the condition that its rate of change is equal to the torque which is applied externally on a system of particles. I showed in the case of a one particle system that this was equivalent to applying the rate of change of momentum is equal to the net external force. We also saw that if dl over dt is equal to tau external and if tau external is 0, this implies that L or the angular momentum is going to be a constant. Let me start this lecture by taking a two particle example and applying this condition to get my answer, and again showing that the result that I get is completely consistent with the momentum equation dp over dt equal to f. So, I would have established through these two examples that it is useful in certain conditions, a particular rigid body rotation, to consider this equation rather than this equation. The example I take is, let me take a rigid massless rod whose one end is fixed at point O and it is free to rotate like this about this point. At the other end of this, I have a mass m2. Let this and this be my x and y coordinates. There is a mass m1 that is traveling in this direction with speed v and it strikes mass m2. What I would like to know is, if mass m1 got stuck with m2, what will be the angular speed of rotation of the system? After all, when mass m1 hits m2, this rod being rigid, it cannot go up and down. The only freedom it has is to move like this. Let me consider the system to be consisting of masses m1 and m2. Then if I look at the rod, the only force that is applied externally on the rod is at this point O, and this gives no torque because the force is not away from the origin. So, about this point O, there is no torque applied, and therefore, if I take angular momentum about point O, it is going to be conserved, and that I can use to calculate the final omega. So, the system I have is this: mass m2, mass m1 coming in with speed v. Let this distance from the x axis be a and let the length of the rod be b. Remember, it is very important that I specify the point O, because angular momentum and torque are origin dependent quantities. So, it is only about point O that the angular momentum is conserved. So, L initial by definition of L is going to be, m2 is not moving, so it does not contribute, only m1 v times a. You can check for yourself, this is equivalent to m1 r1, where r1 is a vector describing the position of particle 1 cross V1, and the direction is going to be into the page. After the masses get stuck and they start moving with speed, angular speed omega, L final is going to be, now the masses m1 plus m2 will be moving with speed omega. So, therefore, the velocity is going to be b times omega, and times b gives me the final L final, which is m1 plus m2 times b square omega. Again, the direction being into the plane of this paper. Equating the two, because tau external is 0, therefore, L final and L initial must be the same, and therefore, I should have m1 plus m2 b square omega is equal to m1 v a, or omega equals m1 v a divided by m1 plus m2 times b square, and that is my answer, which I obtained from the conservation of angular momentum. So, let me write this answer obtained from the conservation of angular momentum, and to be very specific about O. Do I get the same answer if I apply my conventional dp dt equals f? Let us check that. So, remember this answer. Okay? If we do that, let us see what happens. There is a rigid rod and m1 strikes it, the only direction this rod can apply a force on m2 is in this direction. Let us say this force is tension T. Since the rod is rigid, it can withstand any momentum change in this direction, and apply an equal and opposite force to make that momentum 0. So, when this particle comes in with momentum p, it is coming in like this, it strikes mass m2, the component of momentum in this direction will go to 0, because this T would be sufficient to make it 0. It is a rigid rod after all. The only component of momentum that will survive will be this. If I call this angle theta, then this angle is also theta. So, the initial momentum m1 v cosine theta will go to 0 because of this force T applied by the rigid rod, goes to 0, and the only component that will survive, because there is no force in this direction, will be m1 v sin theta, which will be equal to m1 v a divided by b, where a is this distance, as I said earlier, and b is the length of the rod. And this momentum remains the same, but now after the mass m1 gets stuck with mass m2, the mass changes, and therefore, the velocity v prime is going to change, and this is therefore is going to be m1 plus m2 times v prime, where v prime is the new velocity in this direction, and this gives me v prime is equal to m1 v a over b m1 plus m2. So, to recall again, after masses get stuck, this fellow moves immediately after that with velocity v prime, and therefore, omega is going to be v prime over b, which is equal to m1 v a over m1 plus m2 b square, which is the same answer as obtained earlier by applying the conservation of angular momentum. So, the point I am trying to make through these examples is that applying the formula dl over dt equals tau, or its consequence that tau 0 means L is a constant, is equivalent to applying Newton's second law. And therefore, depending on the situation, and particularly in rigid bodies, we are going to use this, which is much more convenient to use. Having developed all the machinery for describing rigid body motion, that is the angular momentum, change in angular momentum, its relationship with the torque applied, and the conservation of angular momentum, now we are ready to apply this machinery to rigid body rotation. We start with simplest of the problems in rigid body rotation, and that is the motion of a rigid body about a fixed axis in space, and for convenience I call it the z axis. The only relevant parameter in this is going to be how much does the body rotate about this axis, because the only thing I am considering is rotation of this body about this axis. So, all the relevant quantities are going to be rotation, about the axis, and component of angular momentum along the axis. Any other component of angular momentum, even if it changes, is sort of compensated for or balanced by the torques applied on the axis to keep it fixed in space. So, right now what we are considering is really the axis is fixed in space and body is rotating about it. I am not even allowing for the axis to translate, that we will consider the next step. So, we are considering a fixed axis rotation with no translation. As I said, other components of angular momentum in this case are compensated for by the torques that I apply to hold the axis in place. The only component is the component of angular momentum along the axis. So, let us first calculate that. So, let us take this as the z axis, this as the x axis, this as the y axis, and the body is rotating like this. Since L is a vector quantity, I also need a convention for its sign. I will take the right hand rule, that is, if I point my thumb in the direction of the axis, the direction of fingers curling give me the positive direction of omega and L, and the other way is going to be negative. So, this way is going to be positive omega and the other way is going to be negative omega. Same thing with Lz, same thing with Lz. So, let us calculate L by definition. Lz is going to be summation I mi Ri cross Vi z component, which is going to be equal to summation I, where I really refers to different points, different masses on this body, mi x I V I yth component minus y I V I x component by definition of the angular momentum. Now, let us look at any point, ith point moving. It is really moving in a circle about this axis. This, as I said earlier, let this be the x axis, let this be the y axis. So, velocity v at any given point is in this direction, phi direction. Recall your planar polar coordinates, and r is obviously in r direction. The magnitude of the velocity, let me make the figure again. This is the rigid body rotating, this is point I is really moving in a circle like this, with this magnitude of the velocity being r, where r is this distance omega. the x component of ith particle is going to be r I cosine of phi, y component is going to be r I sine of phi, velocity is in phi direction, and therefore, ith particle x component is going to be equal to omega r I sine phi with a minus sign, and V I y is going to be omega r I cosine of phi. Recall, Lz is nothing but summation I m I x I V y for ith particle minus y I V x for the ith particle. Substitute all these quantities in. This is going to give you r I square cosine square phi, and this term is going to give you r I square sine square phi with a minus sign. So, minus minus will compensate, and therefore, I get Lz for this body which is rotating about the z axis with omega as summation m I r I square omega, which I can write as summation part inside m I r I square omega, and this we call the moment of inertia. About the z axis. So, let me call this I z omega. This you have seen in your 12th grade, but now I have given you a rigorous derivation starting from the basic definition. I z is nothing but mass times the perpendicular distance from the axis. Remember, r I is this. It is not the distance from the origin, but the perpendicular distance from the axis. Multiply m I times r I square, add it up, that gives you I z, times omega is L z. So, what we found is that given a body which is rotating about an axis, its angular momentum L is going to be given as I omega. I have dropped the axis z, where I is nothing but summation m I r I square, where r I is the perpendicular distance from the axis, or if the mass distribution is continuous, I can write as d m r square. Again, the sign convention is going to be, if I take my thumb in the direction of the axis of rotation, then this curl finger gives me the positive omega. I mean, the thumb is pointing in the positive z direction or positive direction, whichever I choose, and the other way gives me negative. Remember, L is a vector quantity. So, this is equivalent to, when I talk about one dimensional motion, momentum which is a vector quantity could have negative or positive values depending on which way the particle is moving. So, now with this I am now going to illustrate a few things regarding angular momentum, considering this definition of L about a fixed axis. Having discussed angular momentum, now I am going to illustrate how angular momentum really affects the motion or rotational motion in different situations. As a first example, I take this platform which can be freely rotating. So, if I stand on it and start rotating, I will have an angular momentum about the axis. I will show you first the effect of how changing the moment of inertia changes my angular speed in order that the angular momentum remain constant. So, let me stand on this platform, push myself slightly so that I start rotating, and I will take my hands out. You see, I have slowed down. As soon as I take my hands in, I will start moving again. So, let me show it to you again. I rotate myself. As soon as I take my hands out, I slow down. I bring them in, I start moving faster. Maybe the effect is not visible to you because my hands going in and out may not change the moment of inertia so much. So, I have taken two weights to increase my moment of inertia if I move my hands in and out. I will repeat the experiment, and this time the speed change should be visible to you. I stand here, I am not yet rotating, but I want to show you if I take my hands out, since these masses move out, mi Ri square for the masses would increase, the moment of inertia would increase, and therefore the speed should go down if the angular momentum has to remain constant. So, let me rotate myself and I move out. You see, I have slowed down. As soon as I take them in, I move fast. I take them out, I slow down. I take them in, I move very fast. So, this is an effect of conservation of angular momentum. I will in a minute explain it again on the screen, but now let me show you the effect of changing the masses. Now, I will take, instead of light masses, two heavier masses, and you will see that the effect will be much more dramatic, because as I take the masses out or in, because they are heavier, the change in the moment of inertia would be much larger. So, let me do it again for you. I stand here, take my hand out, and I am moving slowly. As I come towards you, I will take my hands in, and you will see I am moving very fast. Again, I will take them out and I start moving slowly. As I put them in, I move very fast. You see the effect of conservation of angular momentum and the change of moment of inertia. Let me explain this on the screen. What we did was, I was standing on this platform which could rotate. Let me stand like this, and I held my hands out with heavy masses here. I was rotating with some angular speed omega. Let me call this omega 1. So, my angular momentum L, as we just derived, was I1 omega 1. As soon as I brought these masses in, I changed to I2, which was I1 minus, let us say, roughly 2 m L square, where m is the mass of each of these and L may be the length of my arm. But however, there is no external torque. This platform is nearly frictionless, and therefore angular momentum must be conserved. So, nu omega, that is I2 omega 2, should be such that the angular momentum remain unchanged. After all, when I am moving my arms in or out, the other forces that are being applied by my joints are internal to the system, and therefore omega 2 becomes I1 omega 1 over I1 minus 2 ml square. As soon as I stretch them out, it again slows down. So, this shows you the effect of change of mass on moment of inertia, change of distance on moment of inertia, and a consequence of the conservation of angular momentum. Now, I take another demonstration in which I will take this bicycle wheel, which I can rotate by my hand. If I give it this rotation, it acquires an angular momentum in the positive z direction if I take this to be the z direction. Let us see what happens if I stand on this platform and give it a rotation. Oh, I start moving. As soon as I stop it, I also stop. Let me give it the rotation the other way. I start moving the other way. Let me stop it and I stop. Let me give it the rotation this way. Stop. Let me give it the rotation the other way. I move this way. Let us try to understand this as to what is happening. What is happening here is that I am standing on this platform, holding this wheel. As soon as I give it a rotation like this, it has gained an angular momentum L in this direction. However, when I apply the force considering myself and the wheel as the system, there is no external torque on the system. After all, this platform is frictionless. So, I and the wheel with me should start rotating in such a way as to develop an angular momentum in the opposite direction of exactly the same magnitude, so that the net angular momentum remains 0, and therefore my body starts rotating the other way. Let me show it to you again. I took this wheel, I stood on the platform, 0 angular momentum. As soon as I give it a rotation in this direction, I start moving the other way. As soon as I stop it, I also stop. I'll rotate it the other way, and then I start rotating the other way. This is a manifestation of the conservation of angular momentum. As a third example of angular momentum conservation, and through this I also wish to show the vector nature of angular momentum, is I take this wheel, stand on the platform, give it a rotation in one direction, I stand on the wheel, and suddenly I'll turn the wheel the other way. That means initially the angular momentum that the wheel has is in this direction. All of a sudden what I'll do is I'll hold it pointing downwards, so that the L would now change direction. If L is a vector quantity and it changes direction like this, the net change in L would be 2 the initial, let me call this L0, 2L0. However, there can be no change in the angular momentum because there is no external torque, and therefore I should start rotating in such a manner that the net angular momentum change is 0. That means I should rotate maybe the other way to keep the angular momentum change 0. Let us see if that really happens. So, I will take this wheel which is rotating, stand on the platform. Right now I am stationary. I will turn this, and you see I start rotating. I will turn this back, I stop. I will turn this again, and I will start rotating. Let me show it to you more clearly by rotating it faster. I stand here, I turn this, I start rotating. I turn this back, I stop. So, this is again a manifestation of the conservation of angular momentum. An effect I would like to show you in this is, if I hold this farther away from the body and then tilt it, or keep it near my body and tilt it, there would be a difference. Hopefully it will be visible to you on the camera, and that I would like you to think about. I will hold it near my body and tilt it. You see the speed. I will now hold it farther away from my body and tilt it. When is it that I should be expecting to move faster, and when is it then I should be expecting to be moving slower? See it again. Hold it near, tilt it, then again give it a speed, hold it far and tilt it. It is really that I am moving the center of mass of the wheel farther and bringing it nearer by holding it farther and nearer, and that makes a difference in my rotation speed when I tilt it. So, let us try to analyze what happened. When I was holding this wheel, let its moment of inertia be I wheel, let it move with the speed omega s, let its mass be m, and let the length of my arms be L, and I was holding it on the platform. When I tilted it, so initial momentum L initial was I wheel times omega s, L final is going to be minus I wheel omega s, because I have tilted it like this. Therefore, I have to start moving. Let my own moment of inertia be I plus there will be a moment of inertia of the wheel ml square, or you can say that the moment of the angular momentum of the wheel is angular momentum of center of mass plus angular momentum of it about its center of mass plus my own angular momentum, and therefore, that gives me minus I wheel omega s plus I plus ml square omega equals I wheel omega s, or omega s final, this will be omega with which I move is equal to 2 I wheel omega s over my own moment of inertia plus m l square from the conservation of angular momentum. Let me also try to understand, when I took this demonstration of having two masses far out and pull them in, why did I start rotating faster? Can I understand this in terms of Newton's laws? Certainly yes. You see, when the hands are stretched out, they are moving with a speed, let us say omega L. As I bring my arms in, the speed goes down because the length or the distance from the axis of rotation has gone down. I have to apply a force on the masses to slow them down. In the process, masses apply force on me to speed me up. The balance gives me the final angular momentum, but you see, doing it this way is slightly more involved, and therefore, the conservation of angular momentum comes in handy to solve this problem. Hopefully by now you are convinced that in rigid body rotation it is the angular momentum that is the key quantity of interest and that determines the dynamics. Let us now see some other quantities or equivalent quantities in rigid body dynamics which are equivalent to one particle dynamics, that will be useful. So, let us look at kinetic energy, and again I am going to consider the simple case of particle moving about one axis. Kinetic energy is equal to 1/2 summation I mi vi square, and therefore, I can write this as 1/2 summation mi ri square, where ri is the perpendicular distance from the axis times omega square, which is nothing but, if I put the bracket here, 1/2 I omega square, which is equivalent to 1/2 m v square of one particle dynamics. What about work energy theorem? Or work done itself? Again we will use the basic definition that work done is nothing but summation f on ith particle, distance moved by it in the direction of the force, dri summed over. So, if a body is rotating like this and I apply a force on this, the only component, since it can move only in phi direction, only component of force that will work is that in the phi direction. So, I can write in this case is summation f I phi direction, where by phi I mean the, in the sense of cylindrical coordinates, this is phi x y and this is the z axis about which this is rotating. F I phi, distance is going to be r I d theta, which is nothing but, this quantity is nothing but the torque. So, torque times d theta. This is going to be partial work done. For full work I put the integration. Once we have determined the work energy theorem is that change in the kinetic energy, that is delta of 1/2 I omega square is going to be equal to work done, which is nothing but tau d theta. Similarly, if I apply an impulse to a single body, what happens to its momentum? Its momentum changes by the amount of impulse f dt. In the similar manner, if I apply an impulse and that provides a torque, its angular momentum is going to change by the torque impulse. So, let us see in the case of rotation about a fixed axis, what are the equivalent quantities of single particle So, let us see what are the equivalent quantities in single particle and rigid body dynamics. So, let me write single particle here and a rigid body. Here I have momentum P, here I have angular momentum. L. Momentum P equals mv, and the case that we have discussed so far, L along a particular axis equals I omega. Momentum satisfies the equation dp dt equals the force. Angular momentum satisfies the equation dl dt equals the torque. If there is an impulse, in that case the change in momentum is equal to the impulse, and in the case of rigid body, if there is an impulse, change in angular momentum is equal to torque impulse. The work done in this case is f dot dx integral. In this case we considered again the case of single axis is tau d theta integral. Kinetic energy is 1/2 mv square. Kinetic energy in this case we derived was 1/2 m I omega square. Work energy theorem tells you that delta K E is equal to work done. Same thing here, delta K E is equal to work done. Having done this simple case, we will make the matters slightly more complicated in the next lecture by considering a combination of translation of a body and a rotation about a fixed axis. We will still call it fixed axis rotation as long as the direction of the axis of rotation does not change, it only translates. Having obtained the expression for Lz as summation I mi Ri square omega, where Ri is the perpendicular distance from the axis of rotation, and we call this quantity the moment of inertia I omega. Let us calculate this quantity I for certain simple and slightly more involved elements. For example, if I have a rod or even a rectangle rotating about the axis here, or this rotating about the axis here, what is the moment of inertia? This is rotating right now, let us say going into the plane or coming out of the plane. So, we can generalize this definition, which we wrote as mi Ri square as equal to integral some mass dm, which is at a distance r square, and integrated over the entire body. For example, in this case, if I take a small strip here at distance x, the width of this strip is dx, then the I for this would be given as integral sigma, I will define what sigma is in a moment, dx times the width of the rectangle times x square, where x square is the square of the perpendicular distance from the axis of rotation of this mass dm, sigma is mass per unit area, which in this case would be the total mass divided by L times W, where L is the total length of the rectangle. The integration is going to be from x equal to 0 to x equal to L. So, let us do that, and when we do that, I get I is equal to integral dx sigma omega x square 0 to L, where I am talking about this rectangle rotating about one of its side, length L, width W. So, this comes out to be sigma W L cube over 3, sigma W L is nothing but the mass. So, m L square over 3, a result that you are well familiar with. As a second example, let us take a ring of mass m and calculate its moment of inertia about its center. Then if I take any mass dm here, all over the periphery the mass is at the same distance from the axis r, and therefore, I is going to be dm the radius square integral, r is a constant, so it comes out to be m r square, another familiar result. As a third example, let us take a disc, a solid disc of mass m and radius r, and I want to calculate its moment of inertia about an axis passing through its center. What I can do for this is divide the disc into small rings. Of width of radius dr. Then the moment of inertia for the disc, I know if its mass is dm, is going to be dm r square, and if I integrate this, it gives me the moment of inertia for the disc. dm is going to be mass per unit area of the disc, which is m divided by pi r square times the area of this small section that I have taken, and this is going to be 2 pi r dr times r square integrated from 0 to r, and what I get is this pi cancels, 2 m over r square times r raised to 4 divided by 4, and the result comes out to be m r square by 2. That is the moment of inertia of a solid disc about an axis passing through its center. The result would easily be generalized to a cylinder also, which is this disc elongated along the z axis. Next example, I take the same solid disc, however, now I take the axis as its diameter. So, this diameter is the axis. For calculating a moment of inertia about this, I will take a strip on the disc like this of width dx, so that its mass is going to be m over pi r square dx times this length, which I will call 2 times y, where y is this length. Multiply this by x square and integrate from minus r to r, because this distance is r. What is y? Y is, you can see from this right angle triangle, is going to be equal to square root of r square minus x square, and therefore, the moment of inertia about one of the diameters is going to be integral from minus r to r m over pi r square times 2 y is square root of r square minus x square times x square dx. Let me take x to be equal to r cosine of phi, that gives you dx is equal to r sine of phi d phi with a minus sign in front, and the limits for this are going to be, for minus r is going to be pi, for x equal to r is going to be 0. With this minus sign, the limits change. In any case, I can write this as, let me write it again. I am talking about the moment of inertia about the diameter. I is equal to m over pi r square times 2 square root of r square minus x square dx. Integral is from minus r to r. I have taken x to be equal to r cosine of phi, and with that this integral changes to pi to 0 with a minus sign in front, m over pi r square times 2 r square minus x square, this will become r sin phi, x square is going to be r square cosine square phi, dx is going to be r sin phi d phi. I have already taken care of minus sign outside, which I can write as this r square cancels, 2 m over pi zero to pi sin square phi cosine square phi d phi, which is equal to 2 m over pi 0 to pi sin square phi cosine square phi d phi, which is equal to m over 2 pi integral 0 to pi sin square 2 phi d phi. Change to variable alpha equals 2 phi, this becomes equal to m over 2 pi 0 to 2 pi sin square alpha d alpha divided by 2. I have forgotten r square somewhere. There was an r square here, so that will remain. There is an r square here, there is an r square here, there is an r square here. So, what we get for the moment of inertia about diameter is m r square over 2 pi integral 0 to 2 pi sin square alpha d alpha over 2, which is equal to m r square over 4 pi integral 0 to 2 pi sin square alpha can be written as 1 minus cosine 2 alpha over 2 d alpha, and this you can see right away is nothing but m r square over 4 pi times pi, which is m r square by 4. A result again you are well familiar with. So, for a disk about its diameter, the moment of inertia is m r square by 4. As last example, let us do a sphere about one of its diameters. For this, what I am going to do is take a cylindrical shell around the diameter, so that the mass of this cylindrical shell is going to be its volume, let us call it dV, times the density, which is going to be m over 4 pi by 3 r cubed, the volume of this cylindrical shell, if I take this to be of radius r and thickness dr, is going to be dV equals 2 pi r dr, and this whole length, let us call it 2y times 2y, where y is this height, which I can write as 4 pi r dr. Y, as we calculated in the previous example, is going to be r square minus r square, and therefore, the mass is 4 pi r dr is square root of r square minus r square times m 3m over 4 pi r cubed. This 4 pi cancels, and therefore, I get as the mass of this sphere as dm equals r dr square root of r square minus r square m over r cubed. This is a cylinder, and therefore, the moment of inertia of the sphere is going to be the perpendicular distance of this is like a ring, is r square times r square root of r square minus r square m over r cubed, or there was a 3 here, times dr. So, this is equal to 3m over r cubed, r varies from 0 to r cube is square root of r square minus r square dr. To evaluate this integral, again I use r is equal to r cosine of phi, so that dr is equal to minus r sine of phi d phi, and limits are going to be from 0 to pi by 2. So, substituting, I am going to get I equals 3m over r cubed integral. Let us see this, this is 0. So, at 0 it is pi by 2 to 0. For r cubed, I get r cubed cosine cubed phi, square root r square minus r square comes out to be r sine phi times minus r sine phi d phi. This r cubed cancels, and I get 3 m r square 0 to pi by 2 cosine cube phi sine square phi d phi. To evaluate this integral, let me write this in a particular way, 3 m r square 3 m r square 0 to pi by 2 cosine phi, cosine square phi will be left, which I will write as 1 minus sine square phi d phi, and let sine phi be equal to z, so that cosine phi d phi is dz, and limits are going to be from 0 to 1, and therefore, the moment of inertia I is going to be 3 m r square 0 to 1 dz z square minus z raised to 4, which is nothing but 3 m r square times 1/3 minus 1/5, which is 2 m r square by 5, and that is the moment of inertia of a sphere about one of its axes. As another example of momentum, angular momentum conservation, let us consider a huge platform which can rotate without friction in one particular direction or any direction. And let us take a person of mass m moving on its periphery with a speed v with respect to the platform. Let the radius of the platform be r and let its mass be m. we want to know with what speed would this platform be moving, with what angular speed would this platform be moving. So, again initially if there is no angular momentum, then L should be equal to 0. If the person moves with respect to the platform in this direction with v, the platform starts rotating the other way with omega, so that the net velocity of the person with respect to ground is going to be v minus omega r, and therefore, the angular momentum of the person is going to be m v minus omega r. On the other hand, the angular momentum of the disk in the opposite direction of the platform is going to be m, capital M, r square by 2 times omega, because this platform is like a disk, and the two should be equal in magnitude because they are opposite in direction, so that the net angular momentum is 0, and therefore, what we get is m v minus omega r times r is the angular momentum. Let us correct it in the previous slide. It should be times r here for the angular momentum, should be equal to m r square by 2 omega, which gives me 2 m v is equal to m r square plus 2 m r square omega, or omega equals 2 m v over m r square plus 2 m r square m v. Oh, there is a r here, m v r, which is nothing but v over r divided by 1 plus m over